about a situation like this, where we have a solid and we're trying to dissolve it in water? This is going to form an equilibrium. We don't normally think of it that way because, back in Chem 2, we just talked about whether something was soluble or not. We didn't talk about how soluble, even though we know good and well that there are limits. We know that if I'm putting sugar in my iced tea, only so much will dissolve. The same is true of salt, even though it's more soluble than sugar. So if we have a situation where we have a salt that should dissolve, it's going to go into an equilibrium. So magnesium hydroxide is one of the weak bases, and we can describe its solubility in different ways, depending on what sort of job we're trying to do with it. We could simply describe how many grams will dissolve in 100 milliliters of solution. We could do a molar solubility and describe how many moles of solute will dissolve in a liter. That sounds more chemistry-like, doesn't it? And we could use, lastly here, the solubility product constant. We often just call it the solubility product. Uh-oh, it's another equilibrium constant. Did we not have enough of these yet? No, we did not. This is talking about if the solution is completely saturated, it won't hold anymore. K sub SP, you know it's bad when we have to go to two subscripts, right? But yet another constant, solubility product. Now, what is it made out of? In this case, it's just going to be the magnesium and the hydroxide, which has to be squared. Why is it just that? Because when we do these types of constants, we ignore solids, so this does not appear. We end up with just the things that it turned into aqueous solution. All right, so the magnesium, the hydroxide, and the hydroxide has to be squared. We are going to do one where we calculate something. It says we're going to do calculating the molar solubility and the solubility in units of grams per 100 milliliters. So we're going to do these first two on this. And what we have is calcium phosphate. Oh boy, that's a nice formula. Well, how is that going to form an equilibrium? Well, it's going to fall apart into 3 calcium ions and 2 phosphate ions. Oh, that's a 3 minus. There we go, AQ. Needless to say, this is not terribly soluble because phosphates don't tend to be soluble, and calcium is not in the first column. So this does not have a very big number for its solubility, the KSP, which we can go look that one up. We'll find it in table A5.4. When we look in that table, we are going to find out that the KSP has a value of 2.07 times 10 to the negative 29. Oh my goodness, that does not sound like very much. Well, what is this constituted from? Well, it's not this because that's a solid. It's only these. It's going to have the concentration of calcium ions, which needs to be cubed. And it's going to have the concentration of phosphate ions, which needs to be squared. So these are what are going to form this. If this falls apart, it is going to form 3 of these and 2 of these. So if I think of X falling apart, now I'm just saying this without writing a rice table, but I'm thinking about it in terms of a rice table. Minus X, if one of these falls apart, 3 of these are going to come into existence. That would be 3X. This would be 2X. Oh. So I should be writing this as 3X cubed and 2X squared. And then you have to remember to distribute these numbers through everything that's inside of the parentheses. So this would be 27x cubed and another 4x squared. All in all, that is 108x to the 5th. Oh my gosh. Okay. But it equals this. So I can work that out. You're going to be very happy your calculator has a button that lets you do this and take a 5th root. That's all I can tell you. You're very happy your calculator works. When your calculator gets done with it, it's going to spit out this number. 7.19 times 10 to the negative 7 moles per liter, because it's molarity that you just got out of this. So this is moles per liter. Oh, well, that was the first thing that I wanted. Since it's spitting out molarity, the molar solubility is given in moles per liter. So I've actually answered one of these already. I did the molar solubility. Now I want the solubility in terms of grams per 100 milliliters. Okay, so I will start with this. Let me just label it. This is your molar solubility. And I want to know what it's going to be in terms of grams, question mark, how many grams per 100 milliliters. What am I starting with? Well, I'm starting with this saturated solution. I'm starting with 7.19 times 10 to the negative 7 moles per liter. Okay, well, this needs to be 100 milliliters. That's not that. Okay, well, 1 liter is 1,000 milliliters, right? That gets rid of that. I've got the right unit down here. That has an extra 0. Okay. What should I do about that? I might have to think about that for a while. That's odd. Maybe I should just turn my attention to the moles and moles and grams. That's easy. I just need the molar mass for that, right? Okay, so molar mass, I can go look it up or I can add it up. I find out it's 310.18 grams per mole. That'll take care of that. Now I can't figure it any longer until I deal with this. How am I going to deal with that 1,000? You know what I should have done? I should have said that 100 milliliters was the same as 0.1 liters. Oh, then the liters will still cancel. This will be per the 100 that I want to do. I will not use this in my calculation because I'm trying to keep it. I will only use the things that are up in the numerator because I'm trying to keep this the way it is so it will match. Okay? That's a little weird. It's not what we usually do. So that's why I'm stressing it here. And then if you do that and you take it through your calculator, you will find out that you get 2.23 times 10 to the negative 5th grams per every 100 milliliters. This is less than you can measure on the balances that we use in our lab. So it'd be like, oh, I dropped a grain on there. Is that enough? It might be. It wouldn't register on the balance, so you wouldn't know whether it was the right amount. You'd have to use a super sensitive balance to even measure how much would dissolve in 100 milliliters of liquid.